Okay, I think I can start. And first, thanks David for the introduction, and thanks Eric and Bob for the organization and the very kind invitation. In this presentation, I'll first introduce our recent work on the interaction between a water drop and hot granular materials. My collaborators, Dr. Dobler, Professor Zhou, and Dr. Wang, will join the discussion session for any question. When a droplet is deposited on a hot solid plate of temperature around the liquid boiling point, the drop boils and quickly vanishes. But if the solid temperature is much higher than the boiling point, the drop is not anymore in contact with the solid but levitates above its own vapor, and the heat transfer is reduced as it can be observed on the lifetime of the droplet. This is the famous Leidenfrost effect. The plate can be substituted by an oil bath, and still the Leidenfrost effect can be observed. Granular materials are more often than not presented to a large audience, as to behave sometimes like a solid, sometimes like a liquid. So the natural question is, what if a drop is deposited on a hot granular material? It's common we see the firemen use water to cool down the wildfire passage. However, the interaction between a drop and hot granular material is still limited. So we developed two setups in order to investigate the drop hot granular bed interaction. The left one we call 3D consisted in a thick cylinder filled with grains. The granular pack was heated from bottom. The right one consisted of a helical cell. We named it a quasi 2D setup. The granular pack inside the cell was heated from the back wall. The cell has a sapphire front wall that allows us to directly observe what happens inside the granular material. For the granular material, we choose silicon carbide because the thermal conductivity is good and is non-oxidable. Here is what we saw with the two setups. At the top, one can see the side view through the sapphire window, and at the bottom, the 45-degree view on the surface of the granular bed in the cylinder. When the temperature is lower than the water boiling point, for example, 80 degrees, the boiling drop only causes a gentle granular splash. Then fast enters the gap among grains. As temperature increases to 120 Celsius degrees, the vaporization of the water drop induces a stronger splash during impact process. A persistent granular fountain can be observed due to the water boil. As temperature increases to 160 and 230 degrees. With the help of 2D setup, we can see the vaporization of the liquid generated a strong vapor flow. The flow expels particles upward and the droplet moves downward. We named this behavior as drop digging. Today, we mainly focus on the drop digging behavior. Let's first have a general view on the drop digging and especially the trajectory of the droplet. Here is a drop forced into a 330-degree granular bed. First, the droplet is at the interface. It takes some time to cross it. Then, in the first 10 seconds, the drop digs at an approximately constant speed, then suddenly stops. However, The grain fountain continues expelling grains for another 10 seconds after digging stop. Next, let's do the digging base for granular bed with a range of temperature. Obviously, droplet has a higher temperature. In higher temperature bed has a low digging speed, which is surprising. We also plot the drop trajectory versus time. H is the depth that droplet has reached. Let's first on the purple curve. We decompose the droplet into 3 steps: air-grain interface crossing, digging, and sending vaporization. As soon as the droplet is below the surface, namely H is on the order of the droplet diameter d, the penetration speed increased and remains constant until the final depth is reached. During motion, particles are absorbed by the droplet. Finally, the drop stops at a depth of H max until the water is completely evaporated. We can extract the time in different regions by the depth droplet reached. We also summarize the time of 3 steps. The total lifetime of the water drop in the hot granular bed is roughly constant, approximately 19 seconds for all temperature, although higher temperature would result in a longer duration to cross the interface and dig downwards. As for the digging speed, we observe that when the temperature is increased, the digging speed decreased, approaching 0. These experiments were also performed for different grain size, and we found that the digging speed increased with the grain size. The fact that the digging speed decreased when the temperature increased is counterintuitive, because one expects that the higher the temperature is, the more vapor is produced. As a consequence, the more grains could be ejected, increasing the digging speed. It's not the case, and we aim to explain this particular behavior. Now, let's try to build a mental idea about how the temperature determines the droplet digging. The experiment results show that the drop digging requires an intermediate temperature. When the grains are too cold, for example, 80 Celsius degree, the drop contact with a lot of grains. The production of vapor is weak. Therefore, the drop cannot dig. On the opposite, when the grains are very hot, we assume the droplet could levitate upon a stable vapor layer. The vapor layer being thick enough to allow the vapor to escape without entraining grains, which is indeed the Leidenfrost state. To sketch the situation, the granular bed is like a solid substrate. The drop has no contact with grains. The intermediate temperature is perfect for drop digging. The vapor gap is of the order of the magnitude of the grain size, and the vapor cannot escape without entraining grains. The droplet can dig. The aim is to explain the decrease of digging speed by a decrease of the production of vapor due to the roughness of the granular material. Indeed, Leidenfrost on rough surface was reported by Kim in 2011. They found that the vaporization rate might decrease when the temperature increased. We propose to model the surface layer of the granular bed has a roughness of R rock. The heat is transferred by two parallel channels through the vapor located between the grains and through the granular network. The vapor channel works on the area contact with vapor, and the granular channel works on the area drop contact with grains. The effective thermal conductivity can be estimated by the weighted average of the two channels. Coming back to the Leidenfrost droplet, we assume that if the wave film thickness exceeds surface layer height, the vapor flow above the grains without wind. Indeed, at very high temperature, it's assumed that the vapor layer is sufficiently thick to flow above the grains and the droplet cannot dig. As experiment observed, the drop digging speed approaches zero at high temperatures. We propose a mechanism for the digging process that is related to the Leidenfrost schemes. Due to the proximity of the droplet to the hot granular bed, under the action of the weight of the droplet, water vapor is generated between the droplet and hot surface. If the substrate were a solid, then the created vapor can generate a thin vapor film. The vapor generated a sufficient vertical force by lubrication to balance the droplet bed. We can obtain the vapor thickness Hc. Then second, we test whether the vapor thickness Hc is smaller than the surface roughness R. If not the case, the droplet cannot dig because the vapor can escape without entraining grains. If it's the case, we calculate the effective thermal conductivity. We can estimate the amount of vapor produced and then obtain the speed of the vapor. When the vapor thickness becomes larger and larger when the temperature increases, the vapor can more and more escape without entraining grains. This is imaged by the parameter phi that allow to estimate the speed of the grains, and eventually the digging speed is obtained by the simple relation, namely the droplet goes down of Hc during the time for a grain to escape from the bottom to the droplet Vg divided by pi r, where r is the droplet radius. By applying this procedure, we have only one parameter, R, which accounts for the roughness of the granular bed. The curve on the figures are obtained by applying the procedure for roughness radius of 68, 69, and 72 micrometer for the grain size 28, 40, and 55 micrometer respectively. The lifetime can also be estimated using this model. However, the model underestimates the total time. This is not surprising because we do not consider the crossing time. This problem is pretty complex to approach. Besides, the model does not consider the eventual trapping of particles inside the droplet, which can limit the vapor production and, on the other hand, might increase the weight of the droplet. We also have some new tries considering the thermal conductivity of the granular material. We observed that drop would bounce on silicon dioxide granular bed instead of digging. The instantaneous high heat conduction and the strong pulsing vapor flow might be the potential for the bouncing behavior. We are still working on it. And that's all. Thank you for listening. And you can also refer our manuscript on physical review phrase.